Now that we've introduced these two concepts related to convergence, we're going to take a detour. This is not something that I would say is certainly a major outcome of this course, but I really need you to see and then hopefully appreciate what conditional convergence is all about, right? Now, some of the results that I'll state in this video are beyond the scope of this course, right? So I'm not going to present any like really advanced proofs, but there's an interesting example that I'm going to show you why conditional convergence is such a important slash interesting, maybe weird property that these infinite series can have, right? So we're going to look at a specific consequence of this. Now, before I get into the details of the video, I just want to, kind of step back and think about what we know about addition, right? And adding up several terms, So for instance, I'm not going to state this very formally, but one of the first properties you learn about the addition of real numbers is that, okay, if a and b are numbers, then a plus b is the same as b plus a, right? And then you can extend this to more than just two terms, So for instance, let's say I have four terms. So a1 plus a2 plus a3 plus a4. Think of all the different ways I could rearrange the sum of these four terms. But that property, right? In fact, the property that I'm referring to is the commutative property of addition. It says I can add these four numbers in any order I want. So I could do a1 plus a3 plus a2 plus a4, and I know I'll get the same result. So basically what I did, I swapped the second and third terms. And if I wanted to, I could then swap the first and fourth. So I could do a sub 4 plus a sub 3 plus a sub 2 plus a sub 1, and so forth. And I'll actually leave it to you to think how many different ways I could do this. So I'll just say, etc. Right? But think about how many ways, right? If you think about the answer, you should tell me how many different ways I can rearrange a sum with these four terms, right? So that's one thing. The other thing, too, that we learn is, let me go back and state it kind of the basic way, right? Is if we have, let's say we have just three terms, right? And it might sound weird for me to say this, but we all have a preferred or a typical way of adding more than just two numbers. In other words, someone could add a plus b first, so do that addition mentally, and then whatever we get from that sum, we add it to c. Or someone maybe likes to do it this way. Group the last two terms, so do b plus c, and then do a plus that result, right? And the interesting thing is this property also could be extended to more, to a summation that has more terms but finitely many, right? So for instance, again, let's say if we had four terms, think of all the different ways now we could not only swap but then group. So I'll write down a few of them. So you could do it the typical way like this, and then after you get that sum of a1 plus a2, you could then take that number and add it to that, to a3. And then after you get that sum, you add it to a4. But it turns out there are other ways that because we can swap things, right? And this property here, the grouping property, can be applied in different ways. Let me just show you another way that it could be applied. Maybe you like to do this, right? You add this pair, take that result, add it to A2, then take that result and add it to A1, right? So you could group them in this particular way. So again, I know this is like, I don't want to feel like I am belittling you by talking about these properties, but you got the commutative property here, right? And then you have the associative property here, right? One is about the order in which we do it. The other one is the way we group things to maybe create a slightly different order. Like we want to indicate a certain precedence, right? That's what grouping does and parentheses does. But for addition, it doesn't matter, right? But what you often don't hear at the lower level is a key concept in that it doesn't matter if you're adding up a finite number of terms, right? So I did 4 here, but this concept could be extended to a summation that has 1,000 terms, right? Or 1,000,000 terms. But what's missing here, again, sometimes, I mean, maybe I should step back and say, I don't hear it a lot when I hear people refer to the commutative property and the associative property, and I certainly don't see it in the textbooks when they state these properties and introduce students to them for the first time. But hidden amongst these properties is the assumption that you're working with finite sums. But now look at you. You are in a second course in calculus, and you're learning about things that are infinite, infinite area, infinite volume, infinite summations, things like that. And it turns out that this assumption of commutativity and associativity does not always apply to infinite sums. So in this video, I'm going to show you, right? I'm going to show you a way that we can take an infinite series that has a certain property, one of the properties that we've explored in previous videos, and show you what happens when you have that type of property. And of course, that property is conditional convergence. All right? Okay, so let's get started on this interesting journey. If you want to tell your friends that, yeah, I'm about to see some math magic, and maybe invite them over, pop some popcorn. Maybe it's not that good, but I think it's pretty interesting when you see what happens. All right, so let's take a look at so we're going to consider a fairly simple alternating series. Let's consider the alternating harmonic series, right? So that's the one that k goes from 1 to infinity, and we have our -1 to the k plus 1, and then we have 1 over k. And again, just as a reminder, I'm going to write out just a couple terms here. So this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus ... right? And if you notice, when you look at this, this would be the standard way of doing it with no particular grouping. And remember what happens in terms of our order of operations. If we were to, let's say, start this summation, and we're just moving from left to right, that's all we would do, because there are no parentheses here that indicate a particular precedence in terms of that order, right? So when it's written like this, it's just saying, okay, we would take 1, and then we would subtract 1/2, and then we would add 1/3, and subtract 1/4, and so on. But we would do that process indefinitely, all right? So first, let's quickly establish, and I think we may have even already done this, but it's again, not a bad exercise to go ahead and do it. Let's go ahead and demonstrate that this, in fact, this series, this alternating series, actually converges conditionally. It doesn't converge absolutely. So let's look at let's see again what happens when we take the absolute value of the terms, right? So if we look at the series of absolute values, so we look at this series, I like working with these simpler ones because again, it's good practice. It gets us using our different tests and recognizing the different series. But when we take the absolute value of the alternating harmonic series, the alternating property goes away. It's no longer alternating. It's now just the harmonic series, which we know is a p-series with p equals 1, and what that means is our harmonic series diverges, right? For a p-series, remember, p has to be greater than 1 for us to get convergence. So this means, so what this means is we do not have absolute convergence. So I'm going to write it like this: does not converge absolutely. All right. So as far as our alternating series, there's this possibility of conditional convergence. So for that, we have to treat the alternating series and apply our alternating series test. And remember, in our alternating series test, we identify these as our positive terms, or a sub k, and we're going to check to see if these terms have two properties, right? So let's write down, so since a sub k is equal to 1 over k, which I can write as also k to the negative 1, here are, let's check decreasing first, right? So let's see if our sequence of terms is decreasing. So again, I like to, for functions like this that are easily differentiated, I like to use the derivative approach. So let's look at a sub k prime. But when I differentiate k to the negative 1, I get negative k to the negative 2, which can be rewritten as negative 1 over k squared. And this derivative is always negative. In fact, I mean, I'm going to say for k greater than or equal to 1, because that's essentially the domain here for our terms, right? But this is technically for all real values of k except 0, right? Because you can't divide by 0. So let's just say for k greater than or equal to 1, our derivative of our terms is always negative. This implies that a sub k is decreasing. And that's one of the things we need for our alternating series to converge. So check mark, all right? And then we have to make sure that, yes, the terms are decreasing, but are they approaching 0? So let me go back up a little more, or scroll down a little more, get some room. So now let's take a limit as k goes to infinity of these terms. Well, again, this is one of our straightforward limits at infinity, that if we have a fraction where the numerator is constant, the denominator is getting arbitrarily large, and that fraction approaches 0. So check mark. So what this means is in fact, I'm just going to write out our statement now. So the alternating harmonic series converges, not absolutely, but conditionally. So converges conditionally. So this is our CC category. We used that in a previous video, right? So the alternating harmonic series converges conditionally, right? So I'm going to write out some terms now. So what this means is, if I take, so I'm going to call this S1. So I'm going to write out, forget about the sigma notation just for a second. So I'm going to write out a few terms, and so now that we have this conditional convergence, we write out a few more here, and then plus 1/9, minus 1/10, and then plus dot dot dot. Then what it means is we can make this sum get closer and closer to a particular number. I don't know what the number is, right? That's kind of the downside of this, right? Unless you know a little bit more about series and so forth, and some tricks that you can do, then you can figure out what the number is. But I'm just going to call that number x, just to say whatever that number is, we know that there's a finite number that this series will converge to. Right? And kind of look at when I look at this, I always look for patterns. So let me illustrate an interesting pattern in this summation. Notice the denominators, right? Since it's just the reciprocal of the positive integers, the denominators alternate between odd and even, right? 1 is odd, 2 is even, 3 is odd, 4 is even. So the signs of the terms alternate between positive and negative, but the denominators alternate between even and odd. So here's what I'm going to do, and here's where you get to see a little bit of math magic. I am going to rearrange these terms in such a way that my arrangement and also my grouping, I'm going to group them in a particular way, is going to produce a number that's different from x. So carefully, I'm kind of telling you the trick in advance. What kind of magician does that? But anyway, we have this arrangement, right, or this order of addition that equals x. I'm going to show you a different arrangement, which involves also kind of a different grouping, right? This one doesn't have any particular grouping because there are no parentheses, but I'm going to rearrange the terms a little bit, group them a little bit. The same terms. I'm not going to change what's positive or what's negative. The terms are going to be the same. It's just the order and the grouping that I'm going to change. And I'm going to show you that I have to end up with something that's different from x, right? Right? Different from x. Okay, so here's my second summation. So this is what I'm going to do. I'm going to start with 1 like this one, but instead of going for the denominators being odd, even, odd, I'm going to go for odd and then even, even. So I'm going to do negative 1/2, and I'm going to swap these two, and then negative 1/4 there, and then bring down the 1/3. So plus 1/3 again, and then what am I going to do? And then I'm going to take the next two terms that have an even denominator. Both of those are negative, so negative 1/6, negative 1/8. Then I'm going to take the next term that has that's not already here, right? Because I'm not going to like duplicate terms, but take the next term that has an odd denominator, and that one's 1/5. I'm just going to do this for a couple more terms. So then I would take the next two terms that have an even denominator. Well, the last one that I had was 8, so that would mean 10 and 12. So I'll say negative 1/10 and negative 1/12, and then plus dot, dot, dot. All right, there we go. So that's my arrangement, right? Now here's my grouping. I'm going to put the grouping in fact, yeah, let me go ahead and write it again. So what I'm going to do is I'm going to group the first pair. So minus 1 minus 1/2, I'm going to group that one, and then I'm just going to bring down the negative 1/4. And then I'm going to group the next pair, the plus 1/3 minus 1/6, and then I'm just going to bring down the next term, the negative 1/8. Then I am going to group the 1/5 and the negative 1/10, and then I'm just going to bring down the negative 1/12, and then that's my pattern. So hopefully you see the pattern, right? So I rearrange the terms so I get odd, even, even, odd, even, even, and then I'm grouping the terms in this particular way. All right. So once I include parentheses, our order of operations says we have to do the parentheses first. So let's simplify what I have in parentheses. 1 minus 1/2 is 1/2. There's no change to the negative 1/4. That comes down. 1/3 minus 1/6 is 1/6. So bring down that 1/6, and there's no change to the negative 1/8. And then 1/5 minus 1/10, that's 1/10. So bring that down. Bring down the negative 1/12, and so on. Okay, that's interesting, but look at what's happened now. Look at my denominators. It's like, uh-oh, where did the odd denominators go? Was that some sleight of hand? I don't know. Well, the thing is now, all these denominators are even. What does that mean? It means they have to have a common factor of 2. So let's go ahead and factor out that, in fact, let's factor out a 1/2. Right? Let's factor out a 1/2. And when I factor out a 1/2 from the first term, I'll just get a 1. Then when I factor out a 1/2 from the negative 1/4, I'll get negative 1/2, and then this will be a positive 1/3 and a minus 1/4 and a positive 1/5 and then a minus 1/6, not 16, 6. Now that would be some interesting magic. That's beyond my capabilities. And then plus dot dot dot. And then look at what we have in parentheses. What we have in parentheses is our original set of terms in that original kind of standard order. Look now back at our denominators. It's even, odd, odd, even, odd, even, odd, even, and look at the signs, right? The terms that have the even denominator those have a negative sign in front of them and so forth. So what this means is what I have in parentheses is essentially what I started in the beginning, and I call that x. I just said because I know it converges conditionally, right? It's going to have to add up to some number, whatever that number is. I'm just going to call it x. But what I have in parentheses now is that same expression in that same order. So this is equal to 1/2 of x. Whoa. So I want you to really think about this for a second. We have one order and one, let's say, grouping that produces a sum of x. And just by rearranging and regrouping, we get that the same terms, right? The same terms, but just a different grouping, a different order, to be equal to 1/2 of x. Right? And then you say, well, x would have to be 0. Like 0 is the only number that would have this property. But we don't know what x is, right? In fact, I mean, I could tell you what the number is. I know what the number is. And again, if I tell it to you, you're not going to believe me, so I'm not going to tell it to you. But in this standard way, the alternating harmonic series, it converges to a certain number, and when we rearrange the term and group the terms in a different way, we now get it to converge to 1/2 of that number. And the only way, right, the only reason why this happens, it has to do with the fact that the series converges conditionally. So the word conditional here is actually referring to the grouping and the order in which we apply or perform our addition. Right? So I'm going to state an important fact here. This is a big result in an area of math called analysis, and it says conditionally convergent infinite series are able to, they are able to converge to different real numbers right, by changing the order and by changing the grouping, right? So different real numbers by changing the order and or grouping of the addition. Right? Again, kind of let that marinate. That's a big deal. That's basically saying the commutative property and the associative property that we hold so dearly, and we use it we don't even think about it the amount of times we use it. Right? If you had $1 for every time you use the commutative property and or the associative property, I guarantee you maybe not a million here, but maybe 1,000, 100,000 here, or here, is that such a thing? But anyway, yeah, so that's the really interesting thing about conditionally convergent series. Now, how does this contrast to the absolutely convergent series? Those are the ones that no matter the order, no matter the grouping, they will always converge to the same number, right? That's the wow factor. I think it's all wow, right? So let me say that here. So absolutely convergent series um, uh, converge to the same sum no matter the order and or grouping of addition, right? So no matter the order and or grouping of addition, right? And that I think is the in fact for me this is the bigger takeaway that I would like you to take away from these few sections, these videos, is what like, and I'd say it this way, what characteristic, right? What's that characteristic that differentiate, not in a calculus sense, but differentiates between a conditionally convergent series and an absolutely convergent series? And it's the idea of, in an absolutely convergent series, no matter how you want to try to change the order of those terms and group them in any kind of fancy way, the result will always be the same sum. The terms will always converge to the same number. Conditionally convergent series, that's not the case. In fact, and I'm going to leave you, this is going to be my closing act of this magical show. This guy Riemann, the one that you can if you don't like calculus and integrals and all these series, if you want to blame one person in history, it's Riemann. Riemann has this fancy. When I proved this theorem for the first time as a graduate student, it I mean, talk about a drop the mic moment. But there is a theorem that says that any conditionally convergent series of real numbers can be rearranged to sum to any real number. Not just the 1/2 that I showed you here, but any real number you want. There is an arrangement of these numbers. In fact, let me go back up here so you can look at our alternating series. He proved, and I know what the proof is like, and we've actually seen different proofs of it over the years, but he proved that for any conditionally convergent series of real numbers, they can be rearranged to sum or to converge to any real number. What that means is, if you wanted to get an answer of pi, there is a rearrangement of these terms that would work. And the reason why is because you have infinitely many of them to play with, right? If you wanted to make it converge to 0, boom, you can do that too. If you wanted to make it, whatever your favorite number is, if you wanted to make it converge to e, or the square root of 2, or 1, or negative 70.8, you could do that, right? But you can only do it if the series converges conditionally. All right, so hopefully your friend that you invited over, the popcorn was good, and the magic show was, hopefully it was okay, but it's getting you thinking about properties that you've done forever, and those properties don't always hold once you enter the realm of infinite series, right? And with that, I'll see you in the next video. And I'm pretty sure I've run out of magic tricks, so we'll just go back to a regularly scheduled program, which involves more calculus. See you then.